Hi, everybody. Welcome to today's masterclass on an overview for deep learning for images and video. I'm really glad you're joining me today. My name is Loren, and I've been at MathWorks over 30 years. I try to share my knowledge, such as classes like today's. You may also find some useful tips for MATLAB from me on the blog I maintain at MathWorks called The Art of MATLAB. So let's get started with this week's topic, deep learning. What I'm trying to make sure that you know is how you could use deep learning perhaps for some of your applications in engineering or science. So here's the agenda. The aim of the session is, again, to provide a clear view of where deep learning is being used in engineering and science. And you might be surprised, it's a lot bigger than broader area than you might think, and how it drives our efforts on their development teams. Also, I would like you to know how you can do research and develop and deploy your own deep learning solutions for the problems that you're working on. And finally, I want you to know what sorts of things MathWorks engineers can do to help support you achieve success with your deep learning problems. So let's get underway. I'm going to head into what's going on with deep learning in science and engineering. Well, I will get to some demos, by the way, so don't fret about that. Deep learning is a key technology covering the current artificial intelligence, or AI, megatrend. Its origins date back to the dawn of computing that evolved to include machine learning, which is now considered to be a part of. Deep learning is part of our everyday lives, as you can see here, from speech recognition used in smart speakers, face detection for cameras on phones, and autonomous self-driving vehicles. You may also have heard of other mainstream applications of deep learning, but how many of them would you consider applicable to the engineering and science domains? One such example is deep learning object detection, which is where a trained deep learning network detector will scan an image or video frame for certain objects. It not only finds the object in the image, but it will draw a bounding box around it, like you can see here. So we can see, you can find, the car and the dog and the bicycle. But that very same technique is being used by Shell to locate tags on different machinery in a location. And by automating this process, it allows Shell to perform efficient maintenance on their equipment. MATLAB is also used in research, and there's a lot of publications coming out with it, from automatic defect detection. Oops, I think I skipped something somehow. I did. MATLAB is being used in industry, before I get to the research, for things like Airbus trying to do automatic defect detection by running a model on an embedded GPU so that the plane itself can do the analysis of whether it's healthy or not. In the automotive area, Denso is modeling, simulating, and deploying models for their complex engine control units. And deep learning is also being used in energy production, for example, by Shell, where it has developed models for earthquake detection using some signal processing techniques. And now we come to MATLAB being used for research as well. Papers are being published showing MATLAB being used for things like automatic detection of cancer from complex medical images, and converting brain waves in ALS patients into words and phrases, which I think is just amazing that people are doing that now. To help you understand how we got where we are today, let's take a look at the MathWorks evolution of deep learning support. I wonder if you know when the first capability of running neural nets was in MATLAB. In fact, it was in the mid-90s with the initial release of the Neural Network Toolbox. When did deep learning itself come to MATLAB? A popular framework, MatConvNet, from Oxford Visual Geometry Group, came out in 2014. But MathWorks first officially started supporting deep learning in 2016. And since then, as you can see from this slide, we've been releasing a stream of major updates just all the time. You may notice that some of these updates relate to the broader area of deep learning. Others, like our apps, focus on productivity. People ask me all the time, what's coming next in MATLAB? And the answer is this field is constantly evolving and changing so much that it's very hard to predict. However, you can see that for each year, we're having an increasing number of updates across a broader and broader area of domains and tools and things like that. I want to point out one thing especially to you, and that is that there's over 200 examples across multiple domains that can help serve you very well, because if you've got a problem that you're thinking of doing and it sounds similar to one of the examples we have, that gives you a leg up in trying to understand how you might apply deep learning to your problem. So here's some very quick technical demos. You see the YOLO, or you only look once, model here, detecting things like signs in the road. If I switch to this next one, you'll see in this case semantic segmentation from SegNet. And what we're doing here is trying to identify in each frame what part is drivable, the green, what vehicles are there in blue, and so that at any given instant, a driver would be able to know, for example, where it could go and where it could not go. Well, that's for images and video, but deep learning can also be used in other domains, and those include signal processing. So on the left, you'll see a human activity detector, if you will, trying to classify whether someone's walking upstairs, downstairs, and so on, based on the sensors on their cell phone. And the second one here, and hopefully you'll be able to hear.
Yes. No.
So what we have here is my colleague Gabriele. He's saying some words that you can see the waveform from here. We're converting those signals, that one-dimensional signal, into a 2D representation, essentially an image sort of view, but it's with a short time Fourier transform or spectrogram. And from that spectrogram, we're using techniques like convolutional neural nets from image processing sorts of areas to then figure out what word he's saying from a catalog of possible words. And an emerging area is reinforcement learning, which is a type of machine learning that uses deep learning very much at its heart. And it has the ability to solve some really hard controls problems, such as teaching a self-driving car how to navigate through traffic, or training a quadruped robot how to walk. Well, why MathWorks and MATLAB for deep learning? So far, I've touched on how MATLAB is focused on engineering and science workflows, but there are some more reasons as well. The next reason is, these are going to go out of order, so I'm going to put them all up. So if I come to the lower left here, the next reason is because we can help you improve your productivity by using interactive apps, which I will show you a little bit going forward, that help expedite the analysis and the data preparation. And it also allows us from these apps to generate reusable code so that we don't have to repeat that task again in the same way. The third reason that might be interesting to you is because our models can be deployed anywhere, from embedded systems to desktop apps to cloud systems as well. Fourth reason why it might be interesting to you is interoperability with open source frameworks such as TensorFlow and PyTorch. This is all done through ONNX connections, or some of it's done through ONNX connections. And then finally, we have an amazing set of people, experienced MathWorks engineers across all kinds of departments, development, training, consulting, who are available potentially to help you. And so hopefully you'll see reasons throughout the talk why why I speak about these advantages of MATLAB and MathWorks. Well, we hear it from our users too. They'll echo those 5 reasons. But recently, the global independent research firm Gartner recognized this as well when MathWorks was named a leader for data science and machine learning platforms for 2020. Our difference is that we understand that success demands that you have not just your model, but a bigger system that's related to it. Success demands more than just your model. And I'm going to come back to that several times here. Many of the other vendors who work on deep learning a lot are really good about delivering an algorithm, but not necessarily in the context of the entire system in which the algorithm is going to live. And you need to incorporate your deep learning across your entire design system workflow to make sure everything is hanging together well. So it's our understanding of that necessity, and even more important, our family of software tools that span that whole workflow that makes such a big difference. Okay. In addition, Gartner also recognized MathWorks as a customer's choice in July 2020, their Gartner Peer Insights Voice of the Customer for data science and machine learning platforms. So that was people speaking up for themselves there. Okay, I want to talk about the workflow that you use now. And I want to get into some of the specifics so that we can then get into a demo that you can begin to sort of understand more details from. Well, the first thing you need to have is data that you prep. And I'll be talking a little bit about that more as we go on. I'm going to talk about all of these a little bit more. The next thing we need to do is develop a model and apply algorithms to it to see if our data can build a model that will predict what's going to happen. Once we make this model, we actually have to check that it's going to do the prediction. So we have to test it and we have to simulate it. And we probably need to put it inside a bigger system so that we can make sure the whole system is working well together. And then ultimately, we need to get it deployed out in the real world. And hopefully through the demonstrations that I'm going to do, you will see pieces of this as we continue on. So I'm now going to go on to developing a deep learning solution in MATLAB. And I'm going to give you a little background on it before I go to the actual code demo. So the featured example is going to be detecting objects with YOLO v2. You only look once. It is a prominent algorithm, and it's particularly a good deep neural network for this task for a few reasons. First of all, it can detect objects in real time because it's fast enough, which makes it versatile for tasks such as autonomous driving and traffic monitoring. Not all neural networks will be performant enough for you to be able to do that. And it's also faster than some other previous deep learning networks that were used for such applications, such as RCNNs or regions with convolutional neural nets. So we're going to step through the different pieces and build an application as we go. So the first thing we need to do is prepare some data. Now, if you didn't get handed data from someone else and you had to go collect it yourself, I'm guessing you have learned that it can be very frustrating when you first work with the data. First of all, you might have data from multiple sources. It could be structured or unstructured. If it's a time span, for example, maybe you're collecting one signal, one channel at one rate, excuse me, and a different signal at a different rate. And you may have noise in the different environments, in fact, different noise for different sensors. And some of the data may be from different domains altogether. And that data needs to be prepared in such a way so that we can actually use it for the modeling stage. And so you might spend a lot of time wrangling with your data. And here I have a great proof point here. Andrei Karpathy talked about this in 2018. While he was doing his PhD work at Stanford, he didn't spend much time on the data at all. He was doing research and focused almost exclusively on creating AI algorithms. Fast forward to now, where he is the director of AI at Tesla. And he says he spends 3/4 of his time on the data because now he's building a car and not a better performing predictor. He may need to develop the predictor from one piece of the car, but he got to make sure that the data is going to support what he's doing. And you may find you end up in that same sort of situation. And I would like to just tell you that I think, from my point of view, MATLAB and Simulink can help make the time that you need to spend on this much more effective and productive. Um, and it's beyond just data manipulation. One of the things that's required for deep learning is something called a labeled data set. So what you need is a set of data for which not only do you have the data, but you have somehow labeled it. So in this particular image, you'll see from a video, we have labeled certain things cars, we've labeled certain things the road, you see barriers from the road, you see the overpass, and so on. Well, I need a whole bunch of information, a whole bunch of examples of data that I've already labeled this way if I want to create a reasonable deep learning model. But as you can imagine, that labeling is very time consuming and can be very tedious, which if we're leaving people like me to do it means it's also going to be error prone because I'll get distracted. And so we have apps that let you help you do that, like the image labeler app that lets you use techniques such as semantic segmentation, similar to what I showed you in that video with the car driving in the UK. And we have apps for many different domains here that you can see. All right, so now I want to come to the data preparation part of my demo. And let me get myself set up. Here's my MATLAB, and I have a script already open. This happens to be a live script. If you don't know what they are, you're not going to hear about them from me today, but basically it's a live notebook that you can use. So even though it looks like a document, it's got real code in it, and I can come here and use it just like any other code, but I can make it pretty so that I can share it with someone else and they understand what I was trying to do. So here's my table of contents. I want to talk about data preparation first. And I need to just configure my project. So I've done that. I'll explain a little bit more what I did in a little bit about that. But basically, if I come to my current folder and I write, whoops, I'm going to open my current folder, and you will see that I have a folder in here that has a whole bunch of images of vehicles. And I could show you that they're vehicles. I don't want to spend a whole lot of time rendering it, but I'll show you if you look carefully. Let me zoom in for a minute. Control 1. You can see that some of these pictures have vehicles in them. Okay, so I've got a whole bunch of data. Now, you know and I know that we could spend time looping through the data to make sure we label the first one and the second one and the third one and so on. But that wouldn't necessarily be the best use of my time. So what I can do instead is I can use the image labeler here. And so what I'm doing is I'm taking all the data and I'm basically saying, I want you to consider all the data as one data set, and it's coming into the image labeler here, which you can see. It's going to take a moment to just get all the data inside there. Okay, and now you can see that I have a frame here. And if we go along here, you'll see I have a whole bunch of different frames. It's going to take a while for them to render here. And what this labeler is going to allow me to do is to figure out a way to actually get some of the cars labeled here so that I don't have to do them all by hand myself. I'll do a few of them, and hopefully we will be able to train an algorithm so that it can find some of them itself. So I'm going to first make a label here, and I'm going to say vehicle. And I'm going to select an algorithm. And what you'll see here is that we have some standard algorithms, and I can add my own algorithm either by importing it or creating a new algorithm. So we've tried to make sure that if we don't have exactly what you want, you've already created what you want, you have a way of tapping into the rest of the tool that way. I'm going to just choose the one with aggregate channel features here. And then I'm going to come in and I'm going to use my mouse, and I'm going to pick a couple vehicles here in the first one, and one vehicle in the second one. Now, I'm pretty sure you don't want to watch me for the next hour label the rest of these images. So what I'm going to do is I'm going to select the rest of them. Automate this because the model I'm starting with already knows some stuff. So we come here and you can see some automobiles are getting automated and some are actually getting missed. I'm not going to go through the whole data set, but I'm going to stop it now. Maybe I have enough data to actually train a network. Maybe not in this case really, but so what I can do is I can say, well, let me come back and see what we found. Well, we missed some, so let me come through and in some cases add a little bit more information. Ooh, I didn't do a very good job on that one. That one's okay. That's way over here. And you see that I can go on and I can modify them if I want to, but I'm going to probably find some in here that are just fine. That's just fine with me. I don't need to necessarily get every one. And I'm going to hit accept. And once I hit accept, I can, for example, view the label summary. And the label summary, well, first of all, you can see I quit after about 40 frames here, but you'll also see that I can come here and we can scan through and I can see ones where I have 0 cars identified. And if I didn't do that quite right, but if I do this quite right in there, it brings me to one that may be a problem and I don't have to go hunt for myself. I can just go do that. And then I could accept it again if I wanted to. And when I get all done, I can say, okay, export this, let's say to the workspace. Maybe I'm going to be using that. I don't know why it always pops behind, but here it is. And if I come to my MATLAB's workspace here now, you'll see I have a ground truth object. And so how do you find the labelers? Well, you saw it on my slide, but if I come to the apps tab, it's pretty easy to look for them. I can click, apps are basically tasks that we let you do interactively when we think that there's some benefit to putting a bunch of steps together that may be somewhat complicated and we can help lead you through in the right order, or just make a tedious task simpler to do and less onerous. But if I look in the apps tab there for the among the apps that we have for all the different products, you'll see that we have a variety of labeling tools. And so if you get to the point where you need to label some data, you should think about looking here to see if it has what you want. You notice there's some for signals, some for images, LiDAR, video, automotive, stuff like that. Okay, let me come back over here. I think I don't need this anymore. I'm going to get rid of this. Save session? No, just trying to clean up as we go. All right, so I'm now going to move on to the second step because I think I showed you that in order to prepare the data, one of the things we need to do is the labeling, and hopefully we have apps that will help support your work with that if you are in the position where you do not yet have adequate label data. Whoops, that was my mouse going wrong. Okay, so now I want to think about what I'm going to do in terms of modeling. And it's really nice to think about the whole set of AI-based algorithms and models. Within the MATLAB environment, you actually have direct access to common algorithms for machine learning and deep learning and reinforcement learning, and then other statistical methods, ones that are used for predictive maintenance, for example, and so on. So this goes all the way from classification and prediction, from regression to deep networks to clustering and so on. And with MATLAB, you can also easily use pre-built models, even if they come from outside the MathWorks ecosystem here. We have ways to import them and read them in. Like YOLO, which is the one that we're going to use today, and we're also going to use ResNet 50. And while algorithm and pre-built models are a good start, it's not enough. And so we have, as I told you before, over 200 examples, and hopefully example in a domain that's close enough to what you're doing where you'll be able to see some hints on things that you might do to help get your project going. Okay. Now, I also talked about apps. I talked about apps for the pre-processing of the data. We also have apps that help you increase the productivity for the design and analysis. Of all the different kinds of neural nets, how do you know which one to do? Or if you're building one from scratch, how do you know how much more you should explore? And so figuring out the modeling that you want can take a long time, and so can the training. And with our pre-built apps that help automate the training and the training step, and they also provide visualization tools. Like here, you can see what the network is for your deep network. So you can access pre-trained models, visualize an imported model, create a model from scratch, analyze the model, import and train if you want into the app, and export and generate code for the task that you did in the app so that you can apply it again later. And in the latest release, there's now an app to manage experiments. Actually, it came out last release, I think. And what experiments allow you to do is explore things like different hyperparameters, because there's some parameters that are not part of your model that may determine how well you've done as a job in terms of fitting your model. And it has to do with things like what step size do you take? And so you can use the experiment manager to help you. And I'm just going to run a small little video here to show you a range of things that you can do. So it lets you explore hyperparameters, such as here. It lets you monitor the training progress, so you can see what's going on here, what's been trained. You can define experiments with MATLAB code. You get to keep track of your work, because often you don't train just one. What you do is you make a bunch of training models with slightly different parameters, and use that to try to figure out which is the best set of parameters when you're all done. And when you figured that all out, then what you do is you go and export the model results that you need so that you can use them again. Okay. So, oops, that's not what I want. Also, training is expensive from a time point of view. Deep learning can take a really long time. And so we have cloud support and third-party integration so that you can move your training to any appropriate platform that you would like here. And we have support for all of them, whether your platform is your desktop, GPU, public cloud, private cloud, and so on. The point is that a single model that I make in MATLAB can be moved to any of these environments, these compute platforms, saving an enormous amount of effort, because you do not need to change anything about the model in order to get the faster acceleration of your training. What you're going to need to do is move your model to the right environment, move any of the code that you need, make sure the data is available there, and then you're free to do the modeling as you go. Well, you may be wondering, that's all well and good, but maybe this takes too long to be worth it for me. We've actually been monitoring and paying attention to performance for a really long time, and we've been continuously improving it, especially in deep learning, where we know things are really important. And you can see we've had major factors of speed up over our releases a couple years ago, both whether you're running on a GPU or a CPU. So we make sure that we're tracking that and doing the best we can to help you with that. Another thing that we do to try to help is make sure that MATLAB can interoperate with all the other frameworks that people might be using for modeling. You are free to do your modeling in MATLAB. We tend to do it in MATLAB ourselves, but we may sometimes take advantage of the ability of MATLAB to import a model from somewhere else that I can use as the basis of building up a model. And we know that the deep learning community is incredibly active and prolific, and new models are coming out all the time. And because we support the ONNX standard, the Open Neural Network Exchange standard, you have access to those new models and can work with them within the MATLAB environment. Okay, so to summarize the modeling step within the MATLAB environment, you can have access to all the algorithms and methods used to develop models. You can work with them at the code level or through an app in most cases, and you can accelerate the training to the appropriate compute platforms. So now I want to come and talk about modeling section here. And what I want to do is see how to train a model to detect the objects that we care about. So I'm going to come back over to my MATLAB here, and I am going to come to my project that I have open, and I'm going to enter my project shortcut and open the modeling. Okay, so we're ready to model. You can see I have an outline for what we're going to do here. And I'm not going to take your time to do the training online or live import the network. If you want to, when you get the code, you can simply check these and do it yourself. I don't have a GPU on the computer I'm on, so it doesn't kind of make sense for me to do that right now, but let me come and go here. And I want to make sure that the data set is loaded. This was output in my live script left over from when my pal Abhijit used it. But it's going to look on my local platform here. And it says, yes, I've got the data here. That's good. And what I need to do now, and this is very common and very important for deep learning, is I'm going to split the data up into a training set for training the detector. I'll use most of the data for that. And then a test set aside for evaluating the detector, because otherwise, how will we know if our detector did any good? Okay, and so I need to have enough data to make a reasonable model, and I need to save enough data to make sure I can actually get enough statistical confidence that my model is doing a reasonable enough prediction. And this is just one way that I can make the split here. I'm going to hold 15% of the data aside for the testing, and the other 85% will be for the training. And as I showed you before, I have that data set, but I really didn't want to have us go through and read in file number 1 and read in file number 2 and so on. So what I did is I'm going to make data stores to point to the data that we have. And I happen to have loaded the data in, some of the data here, and I've got 2 different data stores for training and 2 different data stores for testing. Well, why is that? Well, if we quickly come back to the slide, it's because to train, I need a picture with an image, and I need the bounding boxes in the image. So what I've got here is images with their associated bounding boxes for vehicles in that image. And then the equivalent for the test set 2. I'm going to make sure that I ran this. I am, yes. And I'm going to combine the image and box label structures for the training. I don't need to right now for the testing, into one data store. So it will take with it the image and its related bounding box when it goes to think about what to do with the data. Okay, so now what I want to do is I'm going to clear the output from here on now. And now what I want to do is explore an image here. So I'm reading in an image. Here it is. And I'm rendering it. You can see what I'm doing is I'm taking the first data, that's the image, and I'm showing it. And then I'm taking the annotated image and inserting the rectangular box and then showing the whole thing. So we take our image and then add the rectangle on that we get from it, and then show the annotated image here. So there we have an example. So now that you see how the data is set up, I'm ready to think about creating the YOLO2 object detection network. And the YOLO2 object detection network, which is already out in the wild there actually, can be thought of as having 2 subnetworks. The first one extracts features like where the cars are. And the feature extraction network then, but it's not going to be cars, it's going to be bounded boxes. And then the detection section is going to say in those bounding boxes, was a car found or not? So the idea here is we have a pre-trained network to do the, we're going to use extraction detection here. So the detection, we're going to use ResNet, and we're going to, these labels don't make sense to me. We're going to use the YOLO2. So we have, again, the extraction network is based on a pre-trained convolutional neural net. And it's going to use the ResNet 50 for the feature extraction. And you could use a different network if you preferred. And the detection subnetwork is a small CNN compared with the feature extraction network. Specific, and it's composed of just a few convolutional layers specific to YOLO2. So what I want to do is, let me come over here, is I want to import a network, identify the feature layer, and delete the layers after that feature layer. Now, what I want to do is I want to identify a layer in my network, in my ResNet network, that is the right place to take ResNet 50 and say, that's enough for finding the features we care about. Well, we don't care about minute features. We care about features of a certain size. And so I can sort of make some guesstimates on what that would be in order to help me figure out what I want to do. Before I do that, I'm going to actually find the back end. So this is going to be the extraction part. So I'm going to use ResNet 50 and import it from the Onyx Model Zoo. And again, if you click the box at the top, it will do that for you. It'll show you how to do it. I'm just loading in what I've got around. Now, what I'd like to do now is I'd like to see what this network looks like. Don't you want to look at it? Well, I can come here to one of these apps. If you look in here, here's my apps, and you'll see I have machine and deep learning. I've got some that I've chosen as favorites, and this was near the top, Deep Network Designer. Well, I've got something in my workspace, so let's go and see what it looks like. And it's importing into Deep Network Designer the model that I just imported into MATLAB. And now you can see it's this really long model and it's really hard to read. So let's go zoom in, and let me zoom in a whole bunch until we can start reading something. And when you get in here, you begin to see that this is just made up of essentially blocks that I could have used from over here. Input blocks, convolutional blocks for images, sequence blocks for sequences and signals, activation layers, normalization blocks, pooling blocks, things that allow you to combine blocks, and then output blocks. Things like, well, get me the one that's the highest probability, things like that. And you can see we've colorized them according to what stage they're in or which category they're in. And if I want to look at any given block, I can just click on it and I can find out how it's set. And of course, I can change the parameters. I'm not going to do that here. And I can use this if I want to navigate, and we can see what this network looks as we go down. And if I do some sort of snooping around, what I find is that by the time I've done things like a convolutional kernel, batch normalization, and rectified linear layer, and then repeat that a few times, I get to the point where I've reduced the image from however large it was to a bit smaller, because the depending on how we've done the work. And so what I want to do is I'd like to find a layer that has a resolution where I can still see a car, but it doesn't get much smaller than that. I really don't care about things that would be much smaller than that. And so what I can do here is, I'm going to come back over here, is I can try to figure out, now I've gotten ahead of myself a little bit, but I've got to, I can try to figure out how much of the layers, where I want to cut off the layers. And I kind of want to cut off the layer somewhere around, where did it go? It's somewhere in here. The input of my original images is 224 by 224 by 3. So what we want to do for a good feature extraction layer is look for output features where the width and height are between 8 and 16. And if I go through this network that I just showed you, we want to be downsampled to the point where we have by about a factor of 16. So if I come back to that deep network designer, whoops, over here, it turns out that it's around here at node 140. So what I can do is I can simply come here, and you can imagine cutting off and getting rid of the whole rest of the network there, and using this as the piece of the network that I want to use. Well, I'm not going to do that right now in the Deep Network Designer. What I'm going to do is I'm going to do it in code and load in the modified one as if I'd already cut it. Okay, and now I've got the detection subnetwork, which consists of serially connected convolution, ReLU, and batch normalization layers. And they are followed by a YOLO2 transform layer and a YOLO2 output layer. And we're going to set the convolutional layer filter size to 3 by 3. This is really common in convolutional neural nets, CNNs. And then we're going to build up our detection layers here, which this is the is there some problem? There's batch normalization here, and convolution and batch normalization ReLU. Now, I'm not going to go into a lot of detail here, but basically we have to find anchor boxes so that we know where the basically where the predicted boxes are going to be, where the boxes that may contain these cars are. And I'm going to skip over that at the moment, but there's a bunch of information in the documentation that will explain that there. It might be that other anchor boxes would produce better results, but we got reasonable results looking for boxes at these sizes and locations and aspect ratios. So I'm now going to create and add the last layers. I'm going to use the convolutional 2D layer and the YOLO transform and YOLO2 outputs, like I said. And we're going to add those final layers. And what we also have to do is take the detection layers. Here you can see the detection layers that we've got. And I've added from the original 6, the final convolution and the output layers. And now I need to connect these to my original piece of the network, that piece of the ResNet 50. And so what I'm going to come and do is I'm going to attach my detection layers to the feature extraction layers, which was up to 140, remember, of the first blocks in the YOLO2. And now we've got a detector here, or in ResNet 50 rather. I've got my network here, and I'm just showing you another tool, the Deep Learning Network Analyzer. So this over here on the left is the geometry, the topology of the whole network. Here you can see the node 140 and then what we added on afterwards. And you can see these other networks here. There's subnets here. What you'll see here is we're taking the output from this last layer and having it go through a bunch of different nodes, and also bypassing it. What if we didn't do any of that there? And you'll so you can go through. Now, the nice thing about this is it tells me this particular network, 50 layers. This is really useful. If there is a problem, I can, let's suppose, node 17 was a problem. You'll notice if I click on it, it shows me over here what's going on. And likewise, if I had some warnings or some issues, I could click on them and it would help point me in the diagram to what was going on. So it would be a way of helping me to understand what's going on in my network and possibly help me to debug it if I needed to. Okay, so I'm going to use the detector function, but that we pre-trained beforehand, because again, I don't have the time in front of you nor the right hardware to do this, but my colleague did it. It took about 5 minutes, as you can see here on an NVIDIA Titan X GPU, and I've now loaded it in. Now, remember, I said we wanted to make sure that we could understand how accurate our model was. And so we saved some of the test data here. And you'll see here that I'm going to read in a test image, and I'm going to have it do the detection there and see whether it found what we're looking for. So it's great. It found an image. If it finds an image, if it finds a car, it can annotate it. And I can simply come along here and look to see what I get a great deal of interactivity here in MATLAB. This is partly because of the live control that we have here. And so every time I move the control, it finds the new image and then runs through and does the detection again. So that's not a very systematic way to go, though. And so what you'd like to do is be more systematic about it. And so what I'm going to do is I want to evaluate the detector using the whole test subset. And so I can do that a little more systematically here by running through all the images here. And so I'm going to extract the data, run the detector, compare things. And one way we compare things and understand how well a detector does is to compute something called the precision recall curve. Okay, and I've got recall and precision that came out of this, but it might depend on some other information. So if you'll look here, well, the precision is going to depend on the recall, and we get very high precision, 1, up until a very high level of recall, at which point we're no longer doing as well. Okay, so for the detector is really, really good up until a certain point, and then it just breaks down totally. So in this case, if we needed it to go further, we might need to get additional training data or take longer training it. There's a bunch of techniques we might use there to help ourselves out. Okay. Now, models need to exist within a complete system. I've told you this before, and I told you that was one of our differentiators. And in fact, one of the reasons why Gartner liked the solutions that we had. In an automated driving system, you use the AI for perception, but you still have to integrate it in with algorithms to figure out what path you're going to take through, how you're going to do the braking and acceleration. And not all of those other subsystems may be using AI. They may or may not. It doesn't matter. But they need to be hooked together. And so that's the thing that we do very well. In fact, in this latest release, we've made it even easier for you to work with deep learning networks in your Simulink models, which had been a little bit less comprehensive than it is now. So like I said, your algorithm needs to fit into the entire system here. And so I want to talk about what that means. Well, they need to be able to fit inside a system. So inside somewhere in here, there's going to be, the subsystem that does the perception part. Now, once we get done and we're sure that we have what we want and are ready to think about getting it into the world, we need to think about deploying it. And we have in MATLAB a unique code generation framework that allows models developed in MATLAB to be deployed anywhere without changing the model. Anywhere, from edge devices, embedded devices, desktop, cloud, you name it. This is really important. And if you happen to have gotten your model from an external framework and you imported it into MATLAB through the Onyx framework perhaps, whatever, that imported code, which is part of your model, is also fair game for this deployment piece. Okay, so we can deploy wherever we need to, whether it's sort of edge, embedded, desktop, or cloud. And I want to now come back to MATLAB, and I'm not going to actually create the code right now, but I've got the analysis left over. Oops, I'm doing the wrong thing, part 3. Okay, so we're now thinking about deployment, and we could run this. What you'll see is that we actually have, if I come over here into my project, even if I didn't take that up, you'll see that I have some documentation here. I can bring up a documentation example, code generation for object detection by using YOLO v2, and it goes through and tells you how to take your code from your MATLAB code into being able to run it as, for example, in this case, a MEX file. Well, I'm not going to do that right now, but what I am going to do is I'm going to open up a codegen report. And I'm going to shrink this so it fits it on the screen a little bit better. Okay. And this report got generated when we were creating code for the YOLO2 _ detect. And you can see that this was the code that basically came out of Deep Network Designer. Whatever we did, we take the code, we pass in the input, we annotate the detections in the image if we get a chance. So if I want to run this, what I can do is I can say, give me code insights. No, I don't really want that. Let's look at the entry points. No, I don't want that. What I would like to do is take a look at what happens in here. Well, this is the code that got generated down here from YOLO2 _ detect. So a whole bunch of stuff, and it includes, for example, the GPU code for that. Now this says it's for a MEX file. And we can look at the MEX source because it's a little bit different being a MEX file than standalone code. And we can come through here and I can start to see what's going on. Well, there's a whole bunch of stuff that's going on to work with the GPU. And so eventually we get to the point where we can go through and you can begin to look through the code and see what it's doing. It's doing initialization and the code for actually doing the detection here. And so you can go through and begin to see what's going on. This is the detection piece. And you can start to see where different things happen in the GPU code if you want to see what that looks like. It's nice GPU code, but it's not nice compared to MATLAB code, which is so nice and compact. Remember, our original code was super easy to understand before. Okay. So it's very easy to go into MATLAB and generate code so that you can deploy it to whatever sort of hardware target you'd like. And now I want to talk a little bit about MathWorks deep learning support for you. And beyond just performing the workflow in MATLAB, MathWorks, we feel like your partner. We can help you take advantage of disruptive technologies like deep learning. And when you succeed, that's really something we're very proud of on behalf of what you did. And we would be happy to partner with you to help you to do that. The ways that we can help you are through all kinds of different mechanisms. We can basically help you easily onboard new engineers at your location from different universities and new college grads, provide hands-on sessions to demonstrate a variety of technical concepts, work with you and your data to guide you through deep learning, maybe through consulting. There's potential for on-site, well, not on-site, but online workshops these days. And of course, we have some great technical support available as well. So I want to just reiterate why MATLAB and MathWorks for deep learning. And first of all, whoops, sorry about that. There is the sort of obvious thing that MathWorks has always been involved in solutions for science and engineering. So we always have had that set of domains in our sites. We've been trying to make things easier and more productive, especially if they're tedious tasks or potentially hard to understand, by providing apps and various tools for you to use that will make it easier for you to get the data into the shape that you want or analyze the modeling that you're looking at. Once you do that, you can also grab models and interoperate with models from other systems. You can take your full set of models, your full system, not just the model, but the full system, and deploy it in as many different platforms as you want, from embedded platforms, edge platforms, for example, also, and all the way on up to the cloud. And finally, backed up by a whole bunch of very smart people at MathWorks who are ready, willing, and able to help you. In addition, if this was interesting to you and you don't know much about deep learning, there's a free 2-hour online tutorial, the Deep Learning On-Ramp, that you might look at. You could contact us to see if it makes sense to schedule a deep learning workshop at all. There's some content there about teaching deep learning with MATLAB, and we have some deep learning training. And for some of you who are at campuses that have a full suite with all of the training, you may have access already. You'll be able to find this content. Actually, there's a link in the YouTube page that you're looking at. And so I would like to take this moment to thank you for watching. Please use them to ask some final questions so that you can get them answered. And you'll also notice that there's some links below that may be useful to you, one with the content, and then also 2 others that I want to point out. One for the MATLAB Expo 2020 on demand. It's an online site featuring technical talks covering a broad range of topics where MathWorks products play a central role, and many of them include deep learning as part of it, so you might find some of those interesting. Also, if you're interested to learn more about Simulink, consider entering the Simulink Student Challenge, where you could win $1,000 if you happen to produce the winning entry. And please, don't forget to subscribe to the MathWorks channel to get reminders for the next event. Thank you very much. Do we have any questions coming now? I think you've probably been very well helped by the MathWorkers who are on the channel, who have probably been answering all your questions as you go along. Okay. So one question is, how can we use the YOLO object to further refine a classification? If you want to further refine it, what you might do is you might take the network that you've got and see, well, what happens if I change that from 140 to perhaps a different number nearby, probably, because we thought we got roughly the right resolution. But that's one way that you may want to refine it and see if you can get a more refined classification. I don't know if that's what you mean. If you wanted to do something to differentiate different kinds of objects, for example, another thing you might have meant was, trucks versus cars. Your original data would have had to be labeled like that, and then you would build up a model that had 2 different kinds of classes there. Vehicles, not vehicles, but you'd have cars and trucks, and then you'd go through a similar process that I went through to refine it. But you'd have to start back with the data at that case, and then maybe even roughly the same model we have, but it would have to learn about different kinds of models at that point. Different kinds of classes of data at that point. Okay, then. Well, thank you very much for attending. I hope you got a lot out of it, and I look forward to seeing you next week. Thanks.